back in chapter 1, and we defined a compound as a substance composed of two or more elements combined in a specific ratio and held together by chemical bonds. Some familiar compounds you may see in your daily life would be water, or H2O, and salt, which has a chemical name sodium chloride, which is NaCl. On your own lecture pack, I want you to think of some other compounds that you see in your daily life. What are some other compounds or substances composed of two or more elements that you find in your daily life? Now that we've defined compounds, we're going to start talking about how we create those compounds. So we've talked about how we have all of our elements on our periodic table. We've talked about how those elements are organized, what they're made up of, protons, neutrons, electrons, how we get light out of those, how we get energy out of those, how the electrons are organized. And now it's time to start putting two or more atoms together and creating those compounds. And the first step in doing that is talking about Lewis dot symbols. When atoms form compounds, it is their valence electrons that actually interact. And remember, those valence electrons are the outermost electrons. Okay, they are the ones on our outermost shell. So there's our nucleus. We have our different shells. And the valence electrons are the one in the outermost shell. So a Lewis dot symbol consists of the element's symbol surrounded by dots, and each dot represents a valence electron. So a Lewis dot symbol is how we visualize those valence electrons. So here I have the element boron, element number 5. We see that boron is in group 3A or 13, and therefore we know that it has 3 valence electrons. Those valence electrons are in the 2s and 2p orbitals. In order to draw the Lewis dot symbol, well, we have to show each of those valence electrons around the element symbol. Since there are 3 valence electrons, we show them as 3 dots around boron. Now, you can put those dots in any of those places, okay? So we think of it as, here's our element symbol, which I'm just going to mark as X, and we think of it like a box. And we put our dots on all 4 sides of the box. Now we have to follow our typical rules where we don't pair up our electrons until we have to, so we have to fill up all 4 sides with 1 electron before we add any more. But for elements like boron, where they don't have all 4 sides filled up, you can have different variations that are still acceptable in their Lewis structures. Those are shown down here. Each of these boron Lewis dot symbols all have 3 valence electrons surrounding them, just on different sides of the boron. These are all equally as acceptable Lewis dot symbols for boron because they show all 3 of those valence electrons and they don't show any of the electrons paired up. So the same trends that we see in the number of valence electrons from our previous lessons and electron configurations are the same trends we see in Lewis dot symbols because our Lewis dot symbols are just our visualization of our valence electrons. So here we have group 13 or 3A, which has 3 valence electrons that we just looked at for boron. And we know that every element in group 3A has 3 valence electrons. So their Lewis dot symbol should all be the same, showing those 3 valence electrons, which they all do. If we move to another column, like say group 15 or group 5A, we know that those have 5 valence electrons, and we see that those valence electrons are represented around each of those element symbols, and they each have 5. So if you know the number of valence electrons, you know how many dots to put around your structure. We do have to follow the similar rules as our orbital diagrams when writing our Lewis dot symbols. We first start with placing the electrons unpaired and then pair electrons up. So like I was saying before, we treat it like a box. We put one electron on either side of the box before we start pairing them up. And that way we end up with a maximum number of 8 dots. We cannot exceed 8 dots. Okay, so here we have boron again, which has our 3 valence electrons. When we move to carbon that has 4 valence electrons, we now have a dot on either side of carbon in those 4 positions. When we go to nitrogen, where we have 5 valence electrons, well, there's no other place to put that extra electron because all 4 sides of our box are filled up with 1 electron. So that's when we start to pair up. So we see our electrons pairing here while the other ones are unpaired. So just like our electron configuration and orbital diagram rules, we only pair electrons up when we have to. So if we're able to keep them unpaired in their 4 different positions, that is preferred. What we can't do is this. We can't just make up sides, so we can't just show them like this, like that. We can't do that. That is not allowed. We have to use the box model, where we have to think of it as the 4 different sides. Oftentimes I just see students putting their Lewis dots kind of like a circle around like that. We can't do that either. So for nitrogen we can't have like 2, 2, 2, and 2 and then a 1 randomly because there would still be one side that's unpaired. So as you start to draw these, when we do some practice as well as in your homework, what you should start doing is doing 1, 2, 3, 4, 5, 6, 7, 8. Just start doing that over and over for whatever element it is and going one side each time. And again, I personally choose to do top, bottom, side, side, but if you would like to do side, top, side, bottom, that's totally fine as long as you're following the rule to not pair up electrons until you have to. Okay, now what we're going to use these Lewis dot symbols for is especially useful for when we start talking about ions. So for main group elements such as sodium, so anything in groups 1 and 2, the number of dots is the number of electrons that are lost when creating a cation. So these are cations. So if you look to your periodic table, sodium is in group 1, therefore it has 1 valence electron, and it also prefers to make a cation with a 1 plus charge. So the 1 electron that is being removed from sodium to create that cation is the 1 dot that we see. When we're forming anions in our nonmetals, okay, so for nonmetals in the second period, the number of unpaired dots is the number of bonds that the atom can form. So oxygen here has 6 valence electrons. 2 electrons are paired on top and bottom, meaning that we can make 2 bonds with oxygen. And we'll talk about why that is more both later in this chapter as well as in chapter 6 and chapter 7. So let's do some practice. Let's draw the Lewis dot symbols for the following elements. We have magnesium, Mg, sulfur, S, phosphorus, P, silicon, Si, and bromine, Br. So let's start from the beginning. Mg, magnesium, and I'm going to draw my electrons in red. So magnesium is element number 12. It is in group 2. Therefore, it has 2 valence electrons. So we can draw its electrons as 1 and 2. You could also draw this as magnesium with 1 and 2. Or you can draw those on top and side or the other top and side. You can draw it in many different ways as long as you're showing 2 unpaired electrons around the magnesium. Next up, we have sulfur, S. If we find sulfur on our periodic tables, we see that it is element number 16, and it comes from group 6A. Therefore, it has 6 valence electrons. So, to draw those valence, we're going to do 1, 2, 3, 4. So, my first 4 electrons I have unpaired. Since I have nowhere else to go, my final 2 electrons are going to have to pair up. So, I'm going to do 5 and 6. So, my sulfur has two sets of paired up electrons and 2 sets of unpaired electrons, and I'm still showing all 6 of my valence electrons. Again, a totally acceptable version of this would be 1, 2, 3, 4, 5, and 6, as well as any variation of that, as long as you're showing 2 paired up electrons. I probably shouldn't use dots because that would get confusing. 2 paired up electrons and 2 unpaired electrons. Okay, let's try phosphorus. Block those off. Let's do phosphorus over here. So phosphorus is P. It is a non-metal. It is element number 15 and comes from group 5A. So it has 5 valence electrons. So let's start placing those electrons. 1, 2, 3, 4. I've used up 4. They're all in my 4 positions around my square. Therefore, my last electron is going to have to pair up, and I'm going to put it on the top there. You could have paired it up with any of those unpaired electrons. It does not matter as long as you are showing 5 electrons, 2 of those being paired together, 3 of those being unpaired. Okay, next up we have Si, silicone. Take a second, find silicone on your periodic table. It's right next to phosphorus. It's element number 14 and comes from group 4A. So it has 4 valence electrons. So we have 1, 2, 3, 4. So all of its valence electrons in our Lewis dot symbol are unpaired. Our last example is bromine, Br. Bromine is element number 35 on our periodic table, and it comes from group 7A. So it has 7 valence electrons. So let's start placing those. 1, 2, 3, 4. I've used up my first 4, and all 4 sides of my square are filled. So I need to start pairing up with my last 3. So I'm going to say 5, 6, and 7. So we have 3 sets of paired electrons and 1 unpaired electron. Okay. Now let's work a little bit backwards. Let's say that based on the information provided, let's determine the element and draw its Lewis dot symbol. So we're given some clues here. So we know this element that we're finding in our first problem is in period 4. So look on your periodic table to period number 4. So that's the 4th row down, starting at hydrogen. So your 4th row down starts with potassium. Okay, period 4. And it has a Lewis symbol of X. So we're figuring out what X is. And there's 1 dot on top. So that means it has 1 valence electron. And if it has 1 valence electron, we know that it is in group 1. So if we go to group 1 on our periodic table and go to period 4 in group 1, we see that this element is K, potassium. Potassium is in the 4th row down, 4th period down, and it's in group 1. So the element is potassium, and it has a Lewis dot symbol of K with a dot on top. And that dot can be on the top, the bottom, the side, or the side, as long as there's just 1 electron that is unpaired. Pause the video and try the last 2 examples here. If our element in our second example has 6 valence electrons, we know that it is in group 6A, also known as group 16. So we know our group is in 16, or 6A, and then we're looking to period number 5, so we're looking for the 5th period down. So look to your periodic table, go to the 5th period, go all the way over to group 6A, and I found it to be element Te, or tellurium. Since it has 6 valence electrons, its Lewis dot would be 1, 2, 3, 4, 5, and 6. So we have 2 sets of paired electrons and 2 sets of unpaired electrons. So a period 5 element with 6 valence electrons is tellurium. Our last example tells us that we have 8 valence electrons, so we know we are in group 8A or group 18. Those are the same groups. If it's in period 3, it's in the 3rd row down. So look to your periodic table, go to group 8A, which is the very last column on your periodic table, the one all the way on the right, also known as our noble gases. And if you go to the 3rd row down, you'll see that this element is argon. Argon has 8 valence electrons, so we're going to show its Lewis dot symbol as 1, 2, 3, 4, 5, 6, 7, and 8. As all spots are filled because there's 8 valence electrons. Okay, so we can utilize our Lewis dot symbols to show our ions. So ions can be shown through Lewis dot symbols as they help visualize how the electrons are either added or taken away. So in our example earlier, we had sodium, which has 1 dot because it's in group 1 and has 1 valence electron. That 1 valence electron is in the 3s orbital. And if we want to make this into a cation with a 1+ charge, because elements in group 1 will form a cation with a 1+ charge, giving away their 1 valence electron to form a cation, that 1 electron that's here in sodium will be removed in order to show that the electron was taken away, was removed from the element. So its Lewis dot now just becomes Na with no dots because it has no valence electrons. If there's no valence electrons, there are no dots in our Lewis dot symbol because the Lewis dot symbol shows the valence electrons. When we take away that 1 electron, all we're left with is our core electrons, which we know we do not touch those core electrons at all. So our Lewis dot symbol just becomes Na, but we have to show it with a charge. So you always have to show the charge to show that it is an ion. That charge will also tell you how many electrons were taken away. So cations, when we're showing their Lewis dot symbol, are typically shown with no electrons because all of their electrons are removed in order to create the cation. This is specifically true for groups 1 and 2. For our Lewis dot symbols, we are going to ignore our transitions. We're going to ignore our transition metals because those elements tend to have the valence electrons are in 2 different electron shells, so they get a little bit more confusing where those electrons are coming from, as well as they can have varying charge, which we'll talk about here in a second. So for when we're doing Lewis dot symbols, we're going to ignore our transition metals. So groups 1 and 2, when you show them as being their ions, they will have no dots around them, just like we see with sodium. On the other hand, when we're forming anions, so we'll label this as a cation and an anion. When we're forming an anion, we're showing through the Lewis dot symbol that we've added electrons. So I have the example of oxygen here. And oxygen, in order to form an anion, has to add 2 electrons. Okay, because we always want to get to 8 8 is great. That's what we've been saying for our past few lessons. 8 is great. We want to get to 8 electrons all around because we want to fill up that p orbital. We want to have filled p shells, p orbitals, because filled orbitals make our elements happy. Okay, so in order to fill that p orbital, we have to add 2 electrons. So our Lewis dot, we end up showing it with 2 extra electrons. We add those 2 electrons to our unpaired electrons, so they would show up here and here. We then put that element and its symbol in brackets, and we put the charge on the outside to show how many electrons we added. So anions are typically shown with all 8 electrons around their symbol, since they are adding electrons to fill up their s and their p orbitals. So we want to get that filled p shell, so we're adding the electrons there. So we're showing that we've completely filled up those orbitals. So now these anions have 8 valence electrons in total. So I keep saying 8 is great. 8 is great. Okay, and this rule comes from that law of octaves that we saw back when we learned about how the periodic table was organized. And this became something that we call the octet rule. And according to the octet rule, atoms will lose, gain, or share electrons in order to achieve a noble gas electron configuration. And remember, noble gases have 8 valence electrons. So atoms are going to lose, gain, or share electrons in order to have 8 valence electrons, or to be more like a noble gas. So here we have a metal and a non-metal. So the metal is going to form a cation, and the non-metal is going to form an anion. So the electrons that are lost to create the cation are then gained by the non-metal to create the anion, right? An anion accepts electrons, a cation gives them away. Well, they have to go somewhere, so they have to go to creating the anion. So the metal is giving away 1 electron, and we know that if it gives away its electron, it automatically becomes isoelectronic with a noble gas. Okay, so this becomes more like a noble gas. When the non-metal, or whatever's forming the anion, accepts that electron, it then gets 8 electrons. So this one had 7, it's now getting 8, which we see down here, which is just like a noble gas. So here we are showing that both of these elements, which is a metal and a non-metal in this case, are both just like noble gases. Okay, so they want to be just like the noble gases because noble gases are very stable. When we have a metal and a non-metal that are transferring electrons, this is called an ionic bond. On the other hand, if we have 2 non-metals, they're actually going to share electrons, and that's going to create a bond. So what's happening is they both, in this case, they're 2 non-metals that both have 1 unpaired electron. What they're going to do is share those electrons, which we see here in this kind of Venn diagram looking thing. They're sharing those electrons, so they both end up having 8. This non-metal claims 2, 4, 6, and those as 8. And the other non-metal claims 2, 4, 6, as well as those shared electrons as 8. So whatever is being shared can be claimed by both elements. When we're sharing electrons between nonmetals, this is called a covalent bond. And that's what we're going to be exploring more in this chapter, the difference between ionic and covalent compounds and their bonds. So let's practice writing some Lewis dot symbols for the following ions. So what I suggest doing is writing out the Lewis dot symbol for the neutral atom and then showing or changing it to remove or add electrons accordingly. So let's start with lithium. Lithium is in group 1 on our periodic table, so it has 1 valence electron. If I want to have a 1 plus charge on my ion, I'm going to remove one electron. Okay, so I'm going to show this by just erasing it because I'm able to do that on my iPad. So we essentially just remove that electron. I'll put it back just for visual purposes. So this becomes Li with a plus charge. We always have to show our charge even on our Lewis symbol. We don't show any dots around it because it has no more valence electrons. It removed all the valence electrons to be just like a noble gas. Okay, next up let's look at chlorine, Cl minus. So chlorine is in group 7A on our periodic table, so it has 7 valence electrons. Okay, if we want to create it with a 1 minus charge, that means we're adding 1 electron. Okay, because if it has a minus charge, it has more electrons than it does protons. So we're going to add that last electron right onto the Cl right there. So we get Cl with 8 dots around it. And we put that into brackets with a minus charge on the outside. So now we have a total of 8 valence electrons. Just like a noble gas. Okay, oops. Next up we have strontium, Sr, strontium 2+. Let me bring this down here. So strontium by itself is in group 2. So we have 2 valence electrons, 1, 2. If we're creating it to have a 2+ charge, that means we're removing 2 electrons because a plus charge means I have more protons than I do electrons. In order to do that, the electrons have to be removed. So strontium, in order to create an ion, we just remove both of those electrons and add a 2+ charge. So we're physically just removing those to create that. They're being given away. Okay, now what I want you to do is pause the video and take a second and try our last 2 examples of Lewis dot symbols before we move on to our next topic. So for sulfur is in group 6A. We drew this before, so we know it has 1, 2, 3, 4, 5, 6 valence electrons. If I want it to have a 2- charge, I need to add 2 electrons. Okay, so those 2 electrons are going to go and match up with our unpaired electrons, and we're going to be left with sulfur with 8 dots around it. And then a bracket with a 2- charge on the outside. Finally, we have arsenic, and I believe that this is a typo in my own slides as well as in your lecture notes, but we'll try it both ways. So if we have arsenic 3+, I'm going to move this over here. So if we have arsenic, okay, we have, it's in group 5A, so we have 1, 2, 3, 4, 5 valence electrons. In this version, I have it as a 3+ charge, so 3 of those electrons are being removed. So we're creating As with 1, 2 electrons. So I've removed 1, 2, and 3. Okay, so we remove our paired up ones first. I should probably show that better. So I remove my 1 paired electron first. That's 1 electron. And then we do 2 and 3. So that's how we get our 2 valence electrons there with arsenic 3+. So I would finish this off with a bracket and 3+. Now arsenic is one of those metalloids, so it can be treated like a metal and creating a cation, But it can also be just like a non-metal and create a 3- charge. So that's where I believe my typo came in. I believe this was supposed to be arsenic 3-. So let's try that for arsenic 3-. We had As with 1, 2, 3, 4, 5. And if we're having a 3- charge, that means we're adding 3 electrons. So those 3 electrons are going to go here, here, and here to pair up with our total, our 3 unpaired electrons. So our Lewis dot then becomes arsenic 1, 2, 3, 4, 5, 6, 7, 8 with a 3- charge on the front. So we can show it either way. We can show it as having a 3+ charge and 2 dots, or we can show it with a 3- charge, having all 8. Okay, so as long as you're abiding by the charge, whether there's a typo or not, then you are good.